Astronomy has long relied on the analysis of light to understand the universe. One of the most valuable tools in this endeavor is spectroscopy, the study of how matter interacts with electromagnetic radiation. When light from celestial objects is analyzed through a spectrograph, it can produce different types of spectra. These spectra provide key insights into the composition, temperature, motion, and other physical properties of astronomical objects. The three main types of spectra observed in astronomy are emission spectra, absorption spectra, and continuum spectra. Each of these spectra results from different physical processes and can be used to decipher unique information about celestial bodies. Emission spectra consist of bright lines on a dark background. These spectra are produced when atoms or molecules in a low-density gas emit light at specific wavelengths. The emitted light corresponds to the energy difference between quantized electron energy levels within an atom. When an electron transitions from a higher energy state to a lower one, it emits a photon with an energy equal to that difference, producing a spectral line. Emission spectra are commonly observed in nebulae, which are large clouds of ionized gas. For example, the famous Orion Nebula glows because of the ultraviolet radiation from young hot stars, which excites hydrogen atoms in the surrounding gas. As these atoms recombine with electrons, they emit light at characteristic wavelengths, resulting in emission lines that astronomers can use to determine the chemical composition and physical conditions of the nebula. Different elements produce unique emission spectra, which serve as fingerprints for their identification. Hydrogen, the most abundant element in the universe, has a well-known series of emission lines, such as the Balmer series in the visible spectrum. Helium, oxygen, and other elements also exhibit characteristic lines, helping astronomers identify the composition of distant objects. Another important source of emission spectra in astronomy is active galactic nuclei, AGN. These energetic centers of galaxies, powered by supermassive black holes, produce intense emission lines due to the presence of highly excited gas around them. Similarly, quasars, extremely luminous and distant galaxies, also exhibit strong emission spectra, revealing details about the nature of their energetic processes. Absorption spectra appear as dark lines superimposed on a continuous background of light. These lines occur when light from a hotter source passes through a cooler intervening gas, which absorbs specific wavelengths corresponding to the energy differences between electron energy levels in atoms. The absorbed wavelengths are missing from the spectrum, creating dark absorption lines at specific positions. One of the most famous examples of an absorption spectrum is the spectrum of the Sun. The solar spectrum contains numerous dark absorption lines, known as Fraunhofer lines, first observed by Joseph von Fraunhofer in the early 19th century. These lines are produced by elements in the Sun's outer atmosphere, which absorb certain wavelengths of light emitted from the hotter interior layers. Absorption spectra are particularly useful for determining the composition of stars and galaxies. By comparing observed absorption lines with laboratory measurements, astronomers can identify the elements present in stellar atmospheres. For example, stars with strong hydrogen absorption lines are classified as type A stars, while those with significant calcium lines are classified as type G, like our Sun. In addition to stars, absorption spectra are used to study interstellar and intergalactic gas clouds. When light from distant quasars passes through intervening gas clouds, the gas absorbs specific wavelengths, creating absorption lines that reveal the chemical composition, temperature, and motion of the gas. This technique, known as quasar absorption spectroscopy, has been instrumental in studying the distribution of elements in the early universe. Continuum spectra are broad, smooth distributions of light without distinct emission or absorption lines. These spectra arise from a variety of physical processes, including thermal radiation, synchrotron radiation, and Bremsstrahlung radiation. Thermal radiation, also known as blackbody radiation, is the most common source of continuum spectra in astronomy. A perfect blackbody emits a spectrum that depends only on its temperature, following Planck's law. Hotter objects emit more light at shorter wavelengths, while cooler objects emit more at longer wavelengths. This property allows astronomers to determine the temperatures of stars based on their observed spectra. The Sun, for example, has a nearly continuous spectrum with absorption lines superimposed on it, characteristic of a roughly 5,800 K blackbody. Synchrotron radiation is another source of continuum spectra. This non-thermal radiation is produced when charged particles move at relativistic speeds in magnetic fields. Many astrophysical objects, such as pulsars, supernova remnants, and jets from black holes, produce synchrotron radiation, which is observed across a broad range of wavelengths, from radio to X-rays. Bremsstrahlung radiation, or free emission, occurs when free electrons are deflected by charged particles, such as protons, emitting a continuous spectrum of radiation. This process is common in hot, ionized gases, such as those found in galaxy clusters. The X-ray emission from galaxy clusters, for example, is primarily due to Bremsstrahlung radiation from the hot intracluster medium. The study of astronomical spectra has revolutionized our understanding of the universe. By analyzing emission, absorption, and continuum spectra, astronomers can determine the chemical composition, temperature, density, motion, and other properties of celestial objects. The Doppler effect, for example, allows astronomers to measure the motion of objects relative to Earth. When an astronomical object moves toward us, its spectral lines are blue-shifted, while if it moves away, they are red-shifted. This principle has been used to measure the expansion of the universe, leading to the discovery of dark energy. Spectroscopy also plays a crucial role in studying exoplanets. When an exoplanet transits its host star, some of the starlight passes through the planet's atmosphere, creating absorption lines that reveal the atmospheric composition. This technique has led to the detection of water vapor, methane, and other molecules in exoplanetary atmospheres, providing clues about their potential habitability. Astronomical spectra provide a wealth of information about the universe. Emission spectra help identify elements in nebulae and active galaxies. Absorption spectra reveal the composition of stars and interstellar gas. And continuum spectra give insights into the temperature and physical processes of various celestial objects. By studying these spectra, astronomers can uncover the secrets of the cosmos, from the birth of stars to the nature of distant galaxies. As technology advances, spectroscopy will continue to be a fundamental tool in exploring the universe, helping us better understand our place within it.